Okay. As I said, I'm Jalal, and in this semester, I will be with you in 4 sessions. Let me to use laser pen is better. So it's the first session. I'm with you. I'm working with transformer and the synchronous machine. But end of September and October, I will talk about load flow in 2 sessions. And finally, it will be reactive power control. So I will start with some basic about power electronic, and I focus on the HVDC and how we use power electronic to control active and reactive power in a power system. But this session, I will talk about transformers and synchronous machine. As you know, probably you underwent undergraduate courses about the machine, so you have enough background. But just for recap, in this session, I will talk about transformer and synchronous machine, but both of them have same magnetism background. So anyway, in the machine or transformer, the main important theory is changing, is the movement of the field or the elements. In the transformer, the elements is fixed. You don't have any rotating elements, but the field current, field voltage is AC, is changing. So we have movement. So we can say with the movement with the variation in the field, in the flux, magnetic flux, voltage will be induced in another element. For example, if you have AC voltage in one winding in transformer, since it is AC, you have induced voltage in another winding, in the secondary winding. However, in the synchronous machine, we have rotating element. We have rotor that it's rotating, but the stator is fixed. So since rotator have movement, it can create a cyclic field, magnetic field. So it can create the voltage is induced on the winding of a stator. So it's the general difference between the transformer and the synchronous machine. In the transformer, you don't have any rotating part, but here you have rotor. About the transformer are the link between the generator of the power system and transmission line, and also between the lines. I can show you in this power system, transmission line are operated approximately 700 kilovolt, but the generator work 80-24 kilovolt. Here it is a power plant, but the voltage is approximately 20 kilovolt, but we need to increase the voltage. We do it with a step up transformer. We increase the voltage and send to transmission line to have a higher voltage to decrease the loss in transmission line. And since we have different type of level of voltage in transmission line, we have different substation with a transformer between the lines, and finally in the distribution system, and again in a local transformer that you deliver power to consumer. So you decrease the voltage here. After generator, you increase it. Close to consumer, you decrease. So we use transformer to increase the voltage. So I showed you this video to give you some visualization in your mind to recap the previous courses. But in this presentation, I will go in detail in the maths and how to model and what type of theory are behind this knowledge. So I will start with two winding and ideal transformer. Transformer are consist of two or more coil placed so that they are linked by a same magnetic flux. So you can see here, it is the magnetic flux that is the same for the first coil, or the second coil, or we call it primary, secondary, different. Sometimes it's called high voltage. The next we'll call low voltage. It depends on the condition, but this primary and secondary is more common. In a power transformer, the coil are placed on an iron core here, and in the middle one is the iron core to confine the flux. Here is air, but we want to force the flux to move inside the core. That's why we use the core, iron core. So in the ideal transformer, we can say almost all the flux linking one coil, if the flux passing one coil, the same flux pass another coil. So in the ideal, we don't have any leakage. However, in the transformer, it's important for us to know what kind of relation is between the voltage on both sides of transformer, and what kind of expression we can write for the currents on both sides, and how we can refer, how we can move the impedance from one side to another side. That's why I start with this part. I start with the voltage, and then I will go to the current and the impedance. Now we want to know what's the relationship between voltage on both sides. Suppose that you have the flux that is created by the sinusoidal source. So we can say the flux is sinusoidal and changing in the sinusoidal function. So, but in the ideal transformer, we can say the permeability mu of the core is infinite. So it means that all the flux will be inside the core. We will have no flux outside. And we will be in the core, and the loss will be zero. We have two losses. One of them is for the wires. We can neglect in the ideal transformer, and we have another kind of losses for the iron, for the core, and we can neglect it in the ideal transformer. So suppose that if we have the ideal transformer, we can write E1 is equal V1. You can see there is no resistance here, because we consider ideal transformers, so the resistance is zero. So we can say E1 is equal to V1, and the E2 is equal to V2. E1 is the induced voltage. By changing the flux, when you have the flux here, the voltage is induced here. And V1 is terminal voltage. Usually we call it terminal voltage. We call it terminal voltage. But E1 and E2 are induced voltage. Okay, for the voltage, what kind of relationship is between voltage on both sides? Based on Faraday law, we can say the voltage here, terminal voltage, equal to E1 is the induced voltage. That is N1. It's N1. It's the number of the turn, this winding. And derivative of phi is the flux here. So the induced voltage is proportional to N1, number of turn, and the derivative of phi. And we can write the same equation for the second winding. It's the proportional to the induced voltage in secondary or the second winding is N2 times derivative of flux. And the flux is the instantaneous value, and N1 and N2 are the number of turns for first winding and the second winding. Okay, so according to previous expression, so we know that phi is a sinusoidal function. So we can convert any sinusoidal function to phasor form. And if we divide this expression over this expression, we will have V1 over V2 is E1 over E2 is proportional N1 over N2. You can see if you divided it, because flux is the same for both winding. We have the same flux here. This part and this part will be eliminated, and the V1 over V2 will be N1 over N2. It's a very important expression. And anywhere you can say, for example, if you have transformer, and here is V2, and here is V1. The turn is N1 and N2. If you have this value, you can say V1 is N1 over N2 times V2. So simply we can calculate one side based off another side and the number of the turns in the transformer. And you can see here is the schematic representation of transformer. Is a very simple symbol of a transformer. So you have induced voltage, the turn, the second winding, induced voltage, and terminal voltage. However, what's the relationship between the currents in both sides? In order to calculate the currents on both sides, we use the Ampere laws. So a core is it has background in the magnetism. So we can write this equation, this expression for the every pass, every flux pass. We can say for each pass, suppose that you have a pass that we have flux, or we can use H, that is a magnetic field intensity. If you take integral in this pass, and it's the path we are going. If we take integral, we can take it's the summation of a current that passed through the area. For example, if we have I passing through this path, so we can say integral of h times ds is the whole current passed through this path. So according to this theory in the magnetism, we have the same thing in the transformers, that if we apply these laws, we can write this equation. Because we have the path here, it's the path that flux moving, and we have coil here. And suppose that since we have N2 turn, and here we have N1 turn, we can write this expression, N1 times I1. It's the whole current that encircle the path. Suppose that here is I, again I, again I. So we will have N1 times I. However, since the direction of the current is different, so the direction of the current that's circulating in the winding is different. That's why we use negative here. So we can write it based of the number of turns in the transformer and the direction of the current. However, according to magnetism theory, we can write this equation. However, we know that for every closed path, it's zero. This expression is zero. So we can write this expression in the ideal transformer that we have a closed path. Since we have a closed path and the permeability is infinity, we can write this equation. The right-hand side of equation is zero. According to this expression, we can find the final expression. So if you have a transformer here, it's I1, it's I2. You can, for example, if you have I2, you can calculate I1. But inverse proportional to the turns. It's the relationship between the currents on both sides of transformers. Now we extract the voltage relationship, the current relationship. The next will be the impedance. So suppose that you have an impedance here, Z2, and it is the ideal transformer. And we want to know if we have an impedance here, what will be the measured impedance from other sides? We want to calculate this one. We know that Z2 is, according to phasor domain, is V2 over I2, is voltage over current. V2 is I2 is the terminal voltage on the secondary winding, and I2 is current on that side. We can write this expression for the impedance. However, from the previous slides, we know that how to convert V2 to V1 and how to convert I2 to I1. So if we use the previous expression in the previous slides, we can see that the Z2 prime, that means that the measured impedance from this side will be voltage over the current from this side. And Z2 is the impedance, the secondary side, but you have to use this term to convert it. So anyway, if you want to calculate Z2, you have to use the impedance, but this term is important, is 1 N1 over N2 squared. And N1 is turn of this winding, N2 is turn of this winding. So with this expression, we can convert the impedance from one side to another side. And these three expressions were very important. How to convert voltage, current, and the impedance. These three terms are very important in the analysis of the power system when you have transformer in the line. So now we will talk about practical transformer, non-ideal transformer. Is there any question till now? So if there is no question, we will go further. Okay, so practical. Okay, how do you think to have a short break? Or do you prefer to continue?
Excuse me, I got a question about related to the impedance.
Yeah.
The last slide. Yeah. Why do you say that set to it's not set to prima? It's the derivative.
No, it's just a name. It's the Z prime. You can say, for example, Z. It's Z prime.
Yeah, as the last equation. I mean.
For example, Z3. Yeah. It's not derivative.
Okay. No.
Yeah.
But yeah, you're applying that last equation where you have the pointer. Is the same?
When you have what?
The pointer. The impedance as measured across the primary winding is then that equation. Is the same that you write up there?
Yes. Yes, it is.
Okay.
Any other question? So what's your suggestion? For break or continue? No, any contribution?
I'm okay with both.
Continue. So we can have some more slides and we can have then practical slides or many slides. Okay, I will start with practical transformer. Jump the first or 2 slides, and then we will go to break. Practical transformer or non-ideal transformer. In the non-ideal transformer, the permeability is mu. It's written in this way, is not infinite. So we have inductance, we have some kind of resistance in the magnetism that we show as a inductance. So all the flux will not linking the both winding. We have the leakage, and we have resistance for the winding, and we have losses in the core, because we have a cyclic changing of the flux. So we will have different type of losses in the core. You can see here. Here, R is the resistance of winding, and because of the core, we have some losses. We will talk about that. And we have inductance here. It's the mutual inductance and this self-inductance. For each winding, we have self-inductance, and between two winding, we have mutual inductance. It's because the transformer is not ideal. And we have the same resistance here for the secondary transformer. However, we want to calculate the voltage here and here, V1 and V2. What are these equations in the non-ideal transformer? Now, suppose that we have just one winding with the voltage and the current. So suppose that we don't have this one. We have just one voltage source here, and we have current that circulate in this winding that create flux in the iron core. According to this background, we can write the flux linkage of coil 1 due to the current I1. We have just one current. Remember it's the linkage. We call it linkage flux. That is N1 times phi is phi 1. Phi 1 is the summation of two parts. Phi 1 L plus phi 2 1. If we write this expression for the first winding, it will be lambda 1 1 is the linkage, the flux linkage here, you can see, equals to N1, the number of the turn of first winding, and the phi 1 1. What's the phi 1 1? It's the summation of phi 1L and phi 2 1. So according to magnetism, you learned that before, we can write it is equals to L11 times I1. We call it this parameter is this one. It's the self-inductance of each winding. So, however, when we have current in this winding, we have a same flux that circulate this core and pass this winding. So we have the flux linkage for coil 2 because the flux passed another winding as well. For the coil 2, we can write this expression that lambda 2 1. That means that the linkage flux that passed through winding 2 because of current in winding 1, that will be L2 one that is the mutual inductance, and the current is I1. So when you have two winding transformer and one of the transformer is connected to voltage source, we have current I1. If you have just one voltage and one current, we have two inductance. One inductance is self-inductance, is related to just the first winding. Another one will be mutual inductance that is related to both winding. So we have the same thing for the second winding. In this case, suppose that you have just voltage source here and you apply voltage, but this part is open circuit. You have voltage here and you have current, I2. So we want to evaluate what will be the flux linkage when you have the current just in secondary winding. For the secondary winding, as I explained for the previous, for the primary winding, the flux winding of each coil, here is the second coil, it's lambda 2, 2, is equals to L22 is the self-inductance of this winding, and the current we have here is the self-inductance of coil 2. However, since this current create flux and this flux pass through another winding as well, we have another terms as well, L12. You can see the flux linkage of coil 1 will be lambda 12 is L12 times I2. That this part is called mutual inductance. This mutual inductance is the same with the previous one. So we can say that L12 is equals to L21. It's okay? So is there any question? So if not, we can go further. No, we can have a break. So then we can go. Because after that, we have to calculate when there are two voltage sources on both sides and how to calculate the flux linkage and how to derivative it to calculate the voltage. So I will explain about it later. So 15 minutes break is okay?
Okay.
Okay.